With known questions, let's move to stress concentration. Let's look at the equiaxial case. And what is the equiaxial case? I'll cover that in a second. So here we have a plate that has a circular hole, and then you have these traction loads applied in the far field. And so the question is, what is the stress state right at the hole? What is that stress at the hole in our scenario? And so for that, what we're going to do is something very interesting. We're going to try to take advantage of something that we had discussed before, which is pressure vessels. You can imagine that this could be treated like a pressure vessel with a very small hole where this radius here, or this distance d, that distance d goes to infinity. And so if I have that scenario, and actually the external pressure is applied outwards, you pretty much have the case we're discussing on the right-hand side. So the case on the left is equivalent to the case on the right, because not only you have a hole that's subjected to equiaxial stress, meaning that the attraction stress is applied in the far field, you also can say that this looks like this as this distance d goes to infinity. And so what we can do is use the pressure vessel equations to approximate the solution to this problem. I'll start with the thick pressure vessel analysis. As you can see here, we don't have any internal pressure. The internal pressure here, P naught, is 0. But the external pressure is there, right? So what we can say is that the external pressure is P naught equals minus T, because in our case, we're saying that the pressure is outwards from that surface. And so we treat the problem like a pressure vessel with no internal pressure for a very thick cylinder. In other words, an infinite thickness cylinder where B goes to infinity. Then we can take the external pressure as P naught equals minus T. And so I'll use this very same equation we have used already in the previous example problems. And I'll rewrite it a little bit differently. What I'm going to do, I'm going to cancel out anything that has PI, because there's no internal pressure. And then I'll plug in P naught equals minus T. And when I do that, I arrive to the expression on the bottom here. And I am doing a little trick here. What I'm doing, I'm dividing the numerator and denominator by B squared. And when I do that, I arrive to the expression for radial stress and hoop stress. Let me remind you what the radial stress and hoop stress are compared to the coordinates of the system. So here in this example problem, the radial stress is pointed that way, sigma RR. And then the hoop stress is tangential to the open hole there, sigma theta theta. And so I'm going to use that coordinate system. Now you can see here that because B goes to infinity, and I wrote it in a different way, I basically divide a numerator by B squared and the denominator by B squared. I can write it in a different way, but all these expressions are basically very similar. I'll pause there a couple of seconds to see if there's any questions. Okay. So then I'll go ahead and continue. And what you can see here is, since B goes to infinity, because I have a very thick plate, sorry, a plate that's infinity. So basically this radius to the outer radius is infinity. B goes to infinity. That means these denominators go away. And when I do that, I find that the sigma RR is this expression here, and sigma theta, the hoop stress, is this expression here. And so the question becomes is, where's the highest stress then? Well, obviously, when R is infinity, then sigma theta becomes T, which makes sense because then you're out here in the outside boundary here. But when R is at the hole, you actually get a higher stress for hoop stress. You get that at A equals R equals A, you get that you get 2 times T. While here you're getting 0. So the hoop stress is the highest at the boundary, at the whole boundary. And to make sure that's clear, I'll draw it again. I have a T here, a far field stress of T. And then you have this hole. And what we're saying is that the hoop stress, which is tangential to the hole, that's sigma theta theta. That sigma theta theta at the hole, right at the hole, is 2T. So the stress concentration, in other words, is 2 times the far field stress, which is quite interesting. And so that concludes this particular problem that we have. So we can also start looking at other problems, and I'll go into that in the next one coming up. But any questions so far?